In this video, we're going to look at how to write net ionic equations for double replacement reactions, and also we're going to learn how to predict the formation of a precipitate in a double replacement reaction. So many reactions occur in water. That is, they're in an aqueous solution. They're dissolved in water while they are reacting. So when dissolved in water, many ionic compounds dissociate or separate into their cations and anions. For example, if I have sodium chloride in an aqueous solution here, I actually really have water with a mixture of sodium ions floating around separate from chloride ions because water makes that ionic bond break apart or disassociate. I don't really have sodium chloride in water. I have sodium ions and I have chloride ions. So net ionic equations need to be in a double replacement reaction in an aqueous solution in order to write them. So if I have this double replacement reaction here, silver nitrate and sodium chloride makes silver chloride and sodium nitrate, actually what's happening in an aqueous solution here is that some of these ions are disassociating. I have silver ions and nitrate ions, and I have sodium ions and chloride ions, and then I have a solid sodium chloride. This is actually my precipitate, and I will show you later in this video how you're going to be expected to know that. And then I also have sodium ions floating around with nitrate ions. So these are all ions, and the silver chloride is a solid. So to write a net ionic equation, you get rid of all of the ions that actually didn't do anything. You're just kind of spectating. They were there in the beginning when you mix the reactants together, and they're there at the end when you're done. They're just kind of floating around. They didn't actually react to make our precipitate. So our first spectator ion is nitrate. Nitrate did not make our silver chloride solid. So I'm going to cross off nitrate on the left, and I'm going to cross off nitrate on the right. Okay, sodium is also a spectator ion. Sodium on the left and sodium on the right had nothing to do with the formation of my precipitate, silver chloride. It was there in the beginning on the left as a reactant, and it's there on the end. At the end, it's a product on the right, but it's really just an ion that's just in the solution. It didn't do anything. It's just, we say spectating. It was just kind of watching. It didn't actually take part in the reaction. So I'm left with a silver ion and a chloride ion reacting together to make silver chloride. This is a net ionic equation. So in this whole reaction here, what actually happened, what actually took place in the reaction is this. The silver ion reacted with a chloride ion, made silver chloride. The other ions were there in the beginning, they're there at the end, but they didn't actually take part. So here are the steps to writing a net ionic equation. Step number one is to do the double replacement reaction. Don't forget to assign the charges first. This will make your life easier at the end. Next, identify the precipitate, which is what I'll show you how to do next. Third step is to cross off the spectator ions. Those are the ions that weren't involved in making the precipitate. And then last step is to write the ionic equation showing the ions that made the precipitate. Okay, so how do you predict the precipitate? The precipitate is an insoluble salt, and there's a reference table that can help you with this. There are general solubility rules that are found in table F. So here's table F. It is not the most user-friendly table that we have, but I will show you how to use it here. So what you need to do is start with the end of your compound, the anion of your compound. Put your finger on the chart where that anion is. Then, if the beginning, the cation of the compound in the column to the left or the right is there, you move your finger either to the left or the right. If your finger is in the middle, the compound is a precipitate. A precipitate, remember, is insoluble. So if we wind up in this middle part here, it is an insoluble compound or an exception to a soluble compound. So this middle part here is solid, and I encourage you to actually draw on your own reference table this chart here. Draw it lightly so you don't cover up any of the text, but in the middle here we have solid territory. if when you're done with our little finger trick and your finger winds up on the right, the far right, or the far left, it is a soluble compound or an exception to an insoluble compound. So that means those would be aqueous in solution or liquids. So here's an example question. So magnesium phosphate. So remember, we start with the anion, the ending. Our ending is phosphate, PO4. So we find phosphate on table F, and it's right here. So you put your finger or your pen on phosphate. Now that's in the middle, that's insoluble, but we can't write whether it's insoluble yet, so we check the cation. Our cation is magnesium. We look to the exceptions on the right. So phosphates are insoluble unless they are combined with a group 1 ion or ammonium. Magnesium is not group 1, it's group 2, and magnesium is not ammonium, so we don't move our finger. Our finger stays in the middle, which means, okay, so we don't go over here. We stay in the middle, which means that we are in an insoluble compound. Insoluble means it is solid. It is a precipitate. Next, we have NaHCO3. So our anion here is HCO3, or hydrogen carbonate. Hydrogen carbonate is right here. So we put our finger on the chart here. We check to see if sodium is an exception. There are no exceptions to hydrogen carbonate. So we move our finger back, which means we are a soluble compound. So remember, soluble means this would be aqueous in solution. This would dissolve in solution. Next, we have PbCl2, so we need to find Cl. Cl exists in this little block here with all the other halides. Cl, Br, and I are all in the same group here. So we put our finger here, which means we are outside the solid zone. We're in the soluble zone, but we need to check if there's an exception. And our exception, or our cation, is lead. So lead 2 is an exception, which is what we have. So that means we are an exception to normally soluble things. That means we are insoluble. It's a solid. Okay, so let's put this together in writing our own net ionic equation. So step number 1 is to write the charges. Magnesium is 2 plus and nitrate is -1. Sodium is 1 plus and carbonate, another polyatomic ion from table E, is 2 minus. Next, we need to do the double replacement. In any double replacement, I like to think about it as the two metals switch places. So now I have magnesium with its 2 plus charge is partnering up now with carbonate with its 2 minus charge. And then sodium with its 1 plus charge is now paired up with nitrate with its -1 charge. Our next step is to balance. I need a little 2 over here to balance out the nitrates. 2 nitrates on the right, 2 on the left, and that looks like that's it. I have 2 sodiums, 1 magnesium, 1 magnesium. Okay, now we need to check to see who the precipitate is using table F. So we go to table F, and we are checking both of these. So first we start with the anion, carbonate, CO3 is right here. We need to check to see if magnesium, our cation, is an exception. Magnesium is not a group 1 or ammonium, so we stay in the middle. It is insoluble, which means it is a solid. Just to make sure, we should double check to make sure that this one is soluble. So NO3, nitrate, find nitrate. It is right here. It is soluble, and there are no exceptions, so we stay in the soluble or the aqueous zone here. So now I know that in my products for my double replacement reaction, this is my solid. This is the actual precipitate that's made, and this is going to stay as dissociated ions in solution. Okay, so now that I know that MgCO3 is my solid, I can do my next step, which is to cross off my spectator ions. That is nitrate. Neither nitrate went into making my precipitate, and sodium. Neither sodium went into making my precipitate. I used a magnesium ion, and I used a carbonate ion to make my magnesium carbonate precipitate. So I just combine those together into one equation, and I'm done. There's my net ionic equation. Magnesium plus carbonate makes magnesium carbonate. Let's try this next one. This one's a little harder because it is in words. You need to correctly turn these words into formulas and then do all of the steps that we just did. So go ahead and pause the video and give it a try. Okay, strontium bromide. Strontium is 2+ charge because it's in group 2, and bromine and bromide is -1 charge because it's in group 17. Cross the two, SrBr2 is my first reactant. That will react with potassium sulfate. Potassium is K, it has a +1 charge. Sulfate is a polyatomic ion, SO4, and has a 2- charge. And we need to crisscross that 2 in order to balance the charges. Okay, the charges are all done, so it's time to do the double replacement. So Sr with its 2+ charge is now partnered up with SO4 with its 2-. And we have potassium with its 1+, partnering up with bromide with its 1-. Okay, this equation is not balanced, so we can fix that by writing the 2 here. Okay, I have 2 potassiums, 2 potassiums, 2 bromine, 2 bromides, 2 bromides. Everything else looks balanced. Next, we need to figure out who our precipitate is. So if you got this part wrong, if you didn't write your charges correctly, go ahead and fix that now, and then go ahead and pause it again and try to figure out which one of these two precipitate, or which one of these two products is the precipitate before we write our net ionic equation. Okay, so we're going to check table F. Okay, SO4 is our solid, our precipitate, and KBr is aqueous. So our next step is to cross off our spectator ions, our ions that had nothing to do with the production of this precipitate here, and that would be the potassiums and the bromides. Okay, so our net ionic equation is just the Sr with a 2+ charge and the SO4 with a 2- charge, combining to make SrSO4. So the biggest mistake I see with kids writing net ionic equations is that they don't write the ions. This needs to be an ion to be an ionic equation. If you wrote Sr plus SO4 makes SrSO4, that would be incorrect because we don't have strontium atoms combining with sulfur tetraoxides to make the strontium sulfate. We have strontium ions reacting with sulfate ions. So don't forget, you did all the charges already. Just bring them with you to the final net ionic equation. So in summary here, you should now be able to write a net ionic equation for a double replacement reaction. The steps are pretty easy. It's just like a double replacement reaction, but you need to use table F to figure out which one of your products is a precipitate. Then you need to write the ions that just came together to make that precipitate.